Greetings. My name is Elizabeth Wade. I teach basic calculus in the mathematics department at Pellissippi State Technical Community College. This is topic 2 on derivatives and segment 2.1 on the definition of the derivative. The development of calculus was motivated by the geometry question, what is the slope of the tangent line to the graph of a function at a point P on its graph? Notice that as P changes positions, for example, if I allow P to be located right here, then the tangent line would look like this, and the slope of this piece of red wire that I'm using would be the slope of the tangent. As P moves around the curve, the slope of the tangent is constantly changing. How do we calculate the slope of a tangent line? Notice that the secant line in this diagram intersects the graph at 2 points. I've labeled the point on the left P sub 1. Let's label the coordinates of this point, P sub 1, as x, and then for y we'll use f of x. And then let's move to the right a distance which I'm going to label as h, so that the coordinates of P sub 2, for the x value we would have x plus h. So for y, I would have f of x plus h. The slope of this secant line would be given by the expression. Recall from algebra that to find the slope of a line, you can subtract the y values and divide that by the difference in the x values. So the y values in this case, f of x plus h and f of x, the difference in those would form the numerator of the slope, and then for the denominator, I have this distance from x to x plus h, which would be a distance of h. Notice that if we allow P sub 2, the position of P sub 2, to move closer to the position of P sub 1, that we would obtain a succession of secant lines that approach the position of a tangent line. For example, let's suppose that along the curve I allow P sub 2 to move to this position, which is much closer to P sub 1. Then the original secant line would now look like this. And as I continue to do this, the secant would continue to approach this tangent position. Also notice that as P sub 2 moves closer to P sub 1, that this horizontal distance, which we labeled h, becomes shorter and shorter and approaches 0. Therefore, we can conclude that the smaller h is, the closer the secant becomes to a tangent position. In order to make h as small as possible, we use the concept of a limit and allow h to approach 0. Therefore, the slope of the tangent line to the graph of a function at x is given by this expression. The limit, as h approaches 0, of f of x plus h minus f of x, all divided by h. This expression is called the derivative of f at x and is denoted by f prime of x. Well, that is it for this segment. Now you need to practice this concept by working similar problems. Good luck.